Hi, welcome to my channel. This video covers an introduction to logic circuit analysis. Logic circuit analysis using Boolean algebra. Now, digital circuits operate in the binary number system. All the circuit variables are either going to be a 0 or a 1, and they can also be referred to as a low and a high. And it's this characteristic that makes it possible to use Boolean algebra as a mathematical tool for the analysis and design of digital circuits and systems. Now, Boolean algebra is generally easier to understand than ordinary algebra. The major difference between Boolean algebra and ordinary algebra is that in Boolean algebra, the constants and variables have only two possible values, 0 and 1. So the constants and the variables, again, can only be a 0 and a 1. Now, the Boolean variables represent a voltage level or a state, but are not the actual physical voltage measured in the circuit. A Boolean value of 0 might be assigned to a voltage value between 0 and 2 volts. So if we were to actually go into some circuit, let's just have a block here, and we measured a voltage here, it could be anywhere from 0 to 2 volts, but we're going to say that that is a logic level of 0. And we could measure another part of a circuit, and the voltage there might be measured anywhere between 2.5 and 5 volts, and that will be called a logic level of 1. So the Boolean values 0 and 1 are not the actual voltages, but represent the state of a voltage variable, or what is called a logic level. Now, there are other terms used to describe logic levels. So if we have a logic level of 0, and a logic level 1. Some of the other terms used would be, for logic level 0, we have false, and logic level 1 would be true. Here we have also referred to as off, and logic level 1 would be on. We have low, high, no, yes, open, closed. Since we are only dealing with two values, Boolean algebra is easier to work with than ordinary algebra. There's no square roots, imaginary numbers, exponents. There's just three basic operations. Number one, we have logical addition. Logical addition, which is also called OR addition. Or simply the OR operation. And the common symbol Common symbol is the plus sign. Number 2, we have logical multiplication. And it's also called and multiplication. Or simply I'll put it right here, the AND operation. The common symbol is the multiplication sign, of course. Oops. Multiplication sign. Third, we have logical complementation or inversion. Also called the NOT operation. And the common symbol is an overbar. So it's an overbar. So the three basic logic operations are 1, the OR operation, 2, the AND operation, 3, the NOT operation. So let's go ahead and define each one of these. And we'll start with the OR operation. So with the OR operation, if we have two independent logic variables A and B, and we want to see what the result is when we OR together A and B, so X equal to A or B, we can define the rules of the OR sum of A and B in a table. Now remember, A and B are variables that represent logic variables. So A and B can be either 0 or 1, two possible values. So if we want to sum up OR addition, or the OR operation for A and B, say X equal to A or B. We can put that all in a table for each combination of logic level for A and B. So let's start off with 0, 0, 0, 1, 1, 0, 1, 1. This represents every possible combination. Remember, there's only two possibilities, a 0 and a 1, that A and B can have. Now, OR addition states that X will only equal 0 when both A and B are 0. So for that case, X will equal 0. All other cases, if either A or B is 1, or both are 1, we will have a 1. Now this table is called a truth table, and it's a term borrowed from mathematical logic where they use true and false instead of 0 and 1. So when we use OR addition or the OR operation, these are the rules. X will equal to 0 only when A and B is equal to 0. All other cases, when either A or B are 1 or both are 1, the output X will equal 1. Now there's an electronic symbol for this, and it's called an OR gate, and it looks like this. This is the symbol for the OR operation. We can have two possible inputs, A and B, and the output X will equal to A plus B. Recall or remember that this plus sign does not indicate normal addition. This is the symbol for OR addition, which follows the rules summarized in this truth table. Now this is for a 2-input OR gate, but the same rules apply for any number of inputs. So if we had a 3-input OR gate, one, two, three, and the inputs were A, B, and C. X would equal to A or B or C. And the truth table would look like this: A, B, C, X equal to A or B or C. And we have to write every combination here: 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and on down the line here. X will still be 0 only when A, B, and C are 0. Nice straight lines there. So X will be 0 only for this case. All other cases, when any of the inputs or all of the inputs are 1, there will be an output of 1, or logic level 1. Now if you notice, because we have two possible states, 0 and a 1, if we have n possible inputs, there will be 2 to the n combinations here. So because we had 3, because n is equal to 3, we had 8 possible combinations. So this is the symbol for an OR gate. And to summarize the operation of an OR gate, the output will be a logic 0 only when both inputs are logic 0. When either of the inputs is a logic 1 or both inputs are logic 1, the output will be a logic 1. And for the case where 1 plus 1, the output is a 1, and 1 plus 1 plus 1, the output is a 1. And the easy way to remember that is with logic levels, there's only 2 possible outcomes, a 0 and a 1. So in these two cases, with multiple inputs, if all the inputs or either of the inputs are 1, the output will be a 1. That's the rule or the rules for an OR gate. So now let's go on to the operation of an AND gate. So now let's define the AND operation, or AND multiplication, if we have two variables, two logic variables A and B, and we want to know what the result is, X, and we're ANDing them together, so this dot here is the symbol for multiplication, and we can use a truth table again to define the rules. For the AND operation. And we have here the two variables A, B, and X equal to A and B. We have 0, 0, 0, 1, 1, 0, 1, 1. We will see here that AND operation or multiplication is the same as regular multiplication. X will only equal to 1 when both A and B is 1. All other cases, it is 0. And this can be extended to multiple input AND gates. The symbol for the AND gate this is the symbol. Where we have A and B, and X is equal to A and B. So the important thing to remember here is that AND multiplication is the same as ordinary multiplication, where the output X is only 1 when both input A and B are 1. For all other cases, the output will be 0. And this is the symbol for the AND gate. One last thing, just like ordinary multiplication, with AND multiplication, you don't have to include the dot. It's understood, and you can just keep it out, leave it out. But it's understood that this is multiplication. So now let's go on to complementation or inversion or the NOT operation. So now let's go over the NOT operation. Now the NOT operation is unlike the OR and AND operation in that it can be performed on a single variable. So if we have a variable A, subjected to the NOT operation, the result X would be expressed as X equal to A naught. That's the overbar indicating the NOT operation. So this would be, you would read this as X equals not A. And we can summarize this rule in a truth table with one variable A, and X will equal not A, or A naught. So in the case where we have A equals 0, X will equal 1. And in the case where A is equal to 1, X will equal 0. So X will be the opposite of A. The symbol for the NOT operation, also called an inverter, is this symbol right here. And X will equal A naught. And if the input is A, so you can see here, the output will be opposite the input. So if A is 0, X will be 1. If A is 1, X will be 0. Now, the NOT operation is also referred to as complementation and inversion. That's why we call this also an inverter. So it gives you the opposite of whatever the input is. So finally, let's summarize the three basic operations we just covered. We have the OR operation, and we saw that 0 or 0 is equal to 0, 0 or 1 is equal to 1, 1 or 0 is equal to 1, and 1 or 1 is equal to 1. With AND operation, or AND multiplication, it's exactly the same as ordinary multiplication. We have 0 and 0 equal to 0, 0 and 1 equal to 0, 1 and 0 equal to 0, and 1 and 1 equal to 1. And finally, we have the NOT operation, which inverts whatever's on its input. So if there was a 0 on the input, the output would be not 0, it would be 1. And if there was a 1 on the input, the output would be 0 and not 1. So X is equal to A naught for the inverter. So that covers the three basic operations of Boolean algebra. I hope you found this video interesting. The next video will cover Boolean theorems developed from these three basic operations. So please subscribe and or comment, and thanks for watching.